So we're going to talk about optimal social insurance today. And let me just remind you where we left off in the last lecture with the setup of this model that we're going to discuss today. So we're considering an environment where we have an unemployment insurance system that pays a constant benefit B to agents when they're unemployed. And those benefits are financed by a lump sum tax T of B in the state where you're employed. The government provides insurance subject to the balanced budget constraint that the expected amount of tax revenue it collects equals the expected amount of benefits it pays. And the problem is that we're going to try to maximize the agent's expected utility, which is given by this expression here. So the weighted average of utility in the two states minus the disutility of search effort, which is given by this function psi of e, which is a convex increasing function. Okay, so that's the basic setup of the problem, and we're going to spend most of this lecture talking about various solutions to this problem. So as a benchmark, as in all of these analyses, we usually just start by thinking about what happens in the first best. So first best is the case where there's no moral hazard problem in this case. That is, there's no information problem. Or another way to think about it is that the government can choose both the benefit level and the agent's effort. So there's no issue of the agent choosing effort suboptimally given the government incentives because the government's controlling everything. And so when the government does this, so let's consider the case where the government's choosing B&E jointly to maximize the agent's welfare. And so you're picking B&E to maximize that expected utility function that we had on the previous slide, subject to this balanced budget requirement. And if you just work out the algebra, you'll see that the solution requires having the marginal utility of consumption in the two states equated. And that's intuitive because this is a case where you have actuarially fair insurance. It's fairly priced insurance. And so the agent, we know because of diminishing marginal utility, is going to want to equate marginal utility across the two states. Or if you have the same utility function in the two states, what that means is you want to equate consumption across the two states. In other words, there's no reason not to completely eliminate risk in this environment in the first best. So that's kind of the target that you're trying to achieve if there's no moral hazard problem. Okay, now in practice, you're not going to be able to eliminate the moral hazard problem because effort is unobserved by the government. So fundamentally, all of these the reason we're not able to implement the first best always boils down to some kind of informational problem. And in this case, the informational problem is that you can't see effort. Just like in the Murley's model in the case of taxes, you couldn't see the agent's effort when you're designing the tax system, and so you had to tax on the basis of earnings rather than skill levels, right? It's an analogous problem here. Okay, so why does this generate a problem, and why does this make us want to reduce the optimal benefit level? It's because agents only consider private marginal costs and benefits when choosing effort, and there's a wedge between the private and social marginal product as soon as you have a social insurance system. So the social marginal product of work in this environment is your fixed wage W. You're able to do something like produce some good which someone is willing to pay you W dollars for, so that must be your marginal product. But your private marginal product is W minus B because you know if you go back to work, you give up the unemployment benefit. So if I'm earning $500 a week and I have a UI benefit of $200 a week, I feel as if my net wage is only $300, right? And so as a result, I'm going to search too little for a new job, or I'm going to be too selective in the set of job offers that I accept, and that's going to drive up unemployment rates in equilibrium and thus generate deadweight loss and inefficiency. Okay, so now you can see how a trade-off emerges where we're trying to get to the first best level of insurance, but while we're doing that, we're going to be creating this problem of people working too little, right? Okay, so how are we going to solve for the optimal benefit level given that trade-off? So this is the second best problem. This is really what the focus of this literature is about. So here, effort is not going to be chosen by the government. Rather, it's going to be chosen by the agent to maximize his expected utility, taking B and T of B as given. So that's the critical thing. I don't internalize the fact that when I search less hard, this has an impact on the government budget constraint. And as a result, I end up making a suboptimal choice from a social point of view. It's exactly the same reason that you have deadweight cost in models of optimal income taxation. Same principle. So the agent is solving this problem here, taking t as a fixed number and b as a fixed number, right? So why does that make sense? As a single agent, my behavior is going to have a trivial impact on the government's budget constraint, and so it makes sense that I take a t and b as essentially fixed, right? And so I just maximize my expected utility given the government system. Let's let the indirect utility function that comes out of that problem be denoted by v of bt. So given a benefit tax system, I can calculate what the optimizing level of effort is, and then I can calculate what the level of indirect utility that would be generated is for any given system. And then the government's problem is to maximize the agent's expected utility, taking into account the fact that his behavior is going to respond to the system. So as the planner, what we're trying to do is choose B and T to max V of BT subject to our balanced budget constraint, right? That the expected revenue has to equal the expected cost. So we can write that more precisely as follows. This is really the optimal social insurance problem. It's to maximize the agent's utility. So choose the parameters of the system to maximize the agent's utility, subject to a resource constraint, which is the first constraint here, and an incentive compatibility constraint, which is the second constraint. That the choice of effort, or whatever choices the agent's making more generally, have to be optimal from the agent's point of view. So notice the direct parallel to the optimal taxation problem. It has exactly the same structure. We maximize benevolent social planner, maximizing some objective function of the agent's utilities, subject to a resource constraint and an incentive compatibility constraint. And formally, you can actually think about this problem as an optimal Ramsey tax problem with state contingent taxes. Why is it a Ramsey tax problem? Because we're restricting ourselves to linear instruments here. We're not solving in the more general Merleesian framework for the optimal nonlinear schedule, tipping between the two. Okay, so let's think about how we go about solving this problem. So we've talked many times in this class about different approaches that you can take. Let me just remind you, as in all the other literatures, there are two high-level sorts of approaches that people have taken. One is you can think of as a structural approach, which is to specify a complete model of economic behavior and estimate the primitives of that model. So in this case, we would identify the optimal benefit rate as a function of various primitives of a model of search behavior. So for instance, discount rates, if you're in a dynamic environment, the nature of borrowing constraints, which are very important for determining agents' consumption smoothing ability, the degree of informal insurance, such that when you get unemployed, you might be able to borrow from family members and things like that. So you would estimate all of those primitives, and then in a sense, you would understand how E is chosen as a function of various parameters. And then once you've fully understood that model, you can simulate what happens for different levels of the optimal benefit and just directly calculate what the benefit maximum, what the level of the benefit is that maximizes the agent's expected utility. Okay? A second approach, which is more along the lines of what we've been discussing here, is to derive formulas for the optimal benefit as a function of the reduced form elasticities that people are estimating in the program evaluation literature on social insurance. And so the formula that I'm going to talk about now is one example of this, and then basically in this lecture we'll talk about various ways to solve that formula and connect it to empirical estimates without putting too much structure on what the underlying model is. Okay? So let's talk about how we solve for the optimal benefit level. So we know that at an interior optimum, the optimal benefit level has to satisfy this first order condition where if I perturb the benefit slightly, I don't change the agent's indirect utility. So we want to calculate the derivative of the indirect utility function with respect to the benefit level. So to calculate that derivative, let's write V of B as follows. So it's the maximum level of utility that the agent can attain when he chooses E optimally given the government's tax and benefit system. And here I'm writing really the government only has one choice variable, right? So previously I was writing v of t comma b, subject to the resource constraint, but we know that the resource constraint is going to one-for-one pin down tax rates when I have a benefit level. So I can just write t of b. Given a b, there's going to be a t that's implied by that, by the government budget constraint. And then I can reduce the government's problem to picking this one benefit level, because the tax is going to be automatically implied by that. And so what the government wants to do is pick the level of b that maximizes this function, where this, this part of the function here, E has been chosen to maximize it, based on agent utility maximization, right? So basically, this expression here incorporates the objective function that we had initially and both the constraints that are relevant, okay? Now, since this function has been optimized over E, we know that we can apply the envelope theorem, which then implies that we can ignore the impacts of changes in E on utility, right? Because that's not going to have a first-order effect on the agent's utility. And so we can write dv db as follows. It's 1 minus E times the marginal utility of consumption in the low state. So that's the derivative of this expression. Sorry, did I get this backwards? So yeah, it's the derivative of this expression here on it's the second term. And then when I raise b by 1 unit, I'm going to have to raise the taxes by dt db, and then that's multiplied by E times the marginal utility of consumption in the high state. Okay, so that, so mathematically, what's useful about this is we can ignore the dE dB terms. We've talked about this many times before. It also has a very intuitive interpretation, right? What's the impact of raising benefits by $1 on the agent's utility? There are two terms. First, I give you an extra dollar of benefits when you're unemployed. What's the value of that to you? It's the probability that you're unemployed, 1 minus E, times the value of an extra dollar when you're unemployed, which is U prime of CL, the marginal utility of consumption in the low state. What is the cost of giving you that dollar? I have to take extra tax revenue, extra tax away from you in the high state, dt dB, in order to finance that dollar of benefits. I weight that by the amount of time you're in the high state and the marginal utility of consumption in the high state. Okay, so it makes perfect sense that this is the type of expression you'd get for the marginal value of changing the benefit by $1. Okay, so now let's think about how we actually calculate that. Before I do that, I just want to show you as a slight segue why this is valuable. So we're considering a very simple model here where you're only choosing one thing, your search effort, right? But as the literature has developed since Bailey's 1978 paper, I think what was viewed as one of the weaknesses of the Bailey paper is that it didn't really allow for many margins of choice beyond this very simple effort choice. But what I want to show you next is that this formula is going to be valid even if you have many other considerations in terms of what people might do when they get unemployed. So to take one example, in a recent paper, Greg Kaplan, who's at UPenn, in his job market paper, he documents that many people, when they get unemployed, especially younger workers, tend to move back into their parents' house during the unemployment spell as a way to smooth consumption, right? And so he correctly argues that this is potentially an important channel of insurance that should be taken into account when we're thinking about how to set benefits optimally. Now, what I want to show here is that while that's correct, that will affect the optimal level of unemployment benefits. It's not actually going to affect the formula that we just derived for the optimal level of unemployment benefits. And so in a sense, you don't actually need to change anything to take this mechanism into account. So let's see how this works. So the general point that I'm trying to illustrate here is exploiting these first-order conditions from agent optimization is particularly useful in more complex models than the simple one we were considering before. So take the Kaplan paper. What he does is he takes a structural approach and estimates a dynamic model of the decision to move back in with your parents when you get unemployed. And then he shows how that's going to affect the optimal unemployment benefit level. So let me characterize that in a simpler way here, just to fit it into our notation. The same logic will apply in a more general dynamic model like the one he considers. So to make this very simple, suppose moving home raises your consumption by h because you don't have to pay rent or whatever, right? And it has some cost g of h, so there has to be some cost of moving back home, otherwise you would always move back home and there wouldn't be a, this wouldn't be an interesting problem. So, okay, so now the agent is optimizing over two variables, right? He's optimizing over search effort and sort of how much time to spend at home, which is the h variable. Or there's another dimension, like you can think about it either in a continuous way like I'm doing here, or you can think about it as a discrete decision. Do I move back home or not? And then you're going to be in an extensive margin model where there's going to be a marginal guy who's making that decision, and it's going to basically work out the same way in the aggregate. Okay, so when you just look at this problem, you should see immediately that there's really no difference between E and H in the sense that both of them are going to drop out. The changes in either of those are not going to have a first order effect on the agent's utility. And so because of agent optimization, the formula for dv/db is actually going to be just identical. It's totally irrelevant that you added this h dimension where you get an added h for consumption in the low state at a cost of g of h. That makes no difference. It doesn't affect this formula in any way. But it's important to be clear that this does not mean that the ability to move back home has no impact on the optimal level of unemployment benefits. That's not what we're saying. What we're saying is this formula doesn't change, but the inputs into that formula are going to change as a result of the ability to move back home, right? So in particular, your consumption in the low state is now going to include this part that comes from the ability to move back home, and you need to measure consumption in the right way, and that's going to end up affecting the optimal level of benefits. But if you were measuring consumption in the right way to begin with, you can totally ignore the fact that part of it came from moving back home or doing whatever else. Question? Okay. So that's really the power of looking at the problem in this way, because as you can see, moving back home is, like, in my view, one of many, many things that you might or might not consider when thinking about this problem. Okay. So this formula here is not yet something that we can really take to the data. We have to do a couple more steps. So one problem is that we have these marginal utilities here, not totally obvious how you measure those. We'll come back to that and spend a lot of time on that. The other problem is that we have dt/db here, which is something that we want to translate into empirically estimable parameters, so that's easy. So let's work on that next. So that just comes from differentiating the government's budget constraint, right? How much do I need to raise taxes when I raise benefits by $1? So in order to calculate that, you go back to the government's budget constraint and differentiate with respect to B. And if you just do the algebra, you get one term that's a mechanical effect. That's going to be determined by the ratio of the probability of the two states, right? That determines how much extra I have to raise taxes to fund an extra dollar of benefits. And then there's a second term, which is also familiar from the Ramsey problem, which is related to a behavioral response. And this is the fact that when I raise benefits by $1, the guy is going to start working less, and so I have to raise taxes by more than an equivalent amount. And that embodies the moral hazard cost of providing insurance. So you work out the algebra, and you get an expression that looks like this, which, as you might expect, involves an elasticity of the probability of being unemployed 1 minus E with respect to the unemployment benefit level. And then you plug that back into the expression we had before. I'm not going through the details of the math, but you should do that afterward. dv/db, you plug that in and then factor, and you get an expression that looks like this. Okay? So this is the marginal value of raising benefits by $1. And then remember, at the optimum, we want to go to the point where dv/db equals 0. And that's going to give you then an optimality condition, which is now used widely in this literature, which is the following. So you want to set the gap in marginal utilities between the low and high states, that's the left-hand side, equal to the elasticity of the unemployment rate with respect to the benefit level. So what do I mean by the gap in marginal utilities? So the way you can think about the left-hand side of this expression is that it's the benefit of transferring a dollar from the high state to the low state. So what do you get out of that? You get an extra u prime of CL in the low state. You lose u prime of CH in the high state. And you can think about it loosely as calculating this in percentage terms in some sense. Okay? So that's kind of the value of providing extra insurance. And then that's offset by the fact that you have this distortionary cost because you're changing the amount that people work as you provide this insurance. And so the right-hand side you can think of as corresponding to the cost of transferring that dollar, the budgetary cost above and beyond the, the direct transfer, like what's sort of the leakage from the system. So coming back to your question about the connection to the Ramsey model, the point I was making is that here you have this positive left-hand side. So even though you can levy a complete set of state contingent taxes, you still want to use them in order to achieve this gain on the left-hand side. Okay, so this is the formula that you can see as sort of a starting point for various strands of this literature, a way to organize the literature. So the way I think about it is this is an exact formula for the optimal benefit rate in a fairly wide class of models. But it's not an empirically implementable formula because while I know how to measure what's on the right-hand side, you can see how you might measure the elasticity of the unemployment rate with respect to the benefit level. Those are all empirically measurable concepts. The left-hand side, it's not obvious how you measure it, right? How do you get marginal utilities? So the way I see it, the way to think about literature is how do you identify that parameter on the left-hand side, the value of transferring money across states. And there are three ways so far that people have developed to think about how you identify that gap in marginal utilities. The first is using data on consumption. The second is using data on reservation wages. And the third is a decomposition into moral hazard and liquidity effects, which is kind of analogous to a Slutsky decomposition. We'll come to that in a little bit. So let's start by talking first about the consumption-based approach. Yep.
Is there an intuitive way to think about why it's only U prime and CH in the denominator? It's something like a normalization.
It's a normalization. No, you're right. So there's actually no deep reason for that. It's the point at which you take the Taylor approximation that's driving the U prime of CH being there as opposed to U prime of CL. Okay? So where that's going to matter is the way in which you define the drop in consumption. What you put in the denominator there, I'll show you that in a second, but you're right, there's no strong reason for that. Okay, so let's write the gap in marginal utilities using a, so first we start with a consumption-based formula. The first thing we do is write the gap in marginal utilities using a Taylor expansion. So U prime of CL minus U prime of CH can be written as U prime prime of CH. This is the point I was making, the point at which you're taking the Taylor approximation, times the change in consumption across the two states, right? So just the difference in marginal utilities is given by the slope times the change in the x variable, the change in consumption. So next, let's define the coefficient of relative risk aversion. That's a measure of the curvature of the utility function, right? As minus U prime prime of C divided by U prime of C times C. So just so people are clear on this, that is the elasticity of the marginal utility of consumption with respect to consumption. Okay. So all of these things are the same. The formula that's on the slide and this d log U prime of C, d log C, or in other words, how elastic is the marginal utility of consumption with respect to consumption? So when I raise your consumption by 1%, in percentage terms, how much does your marginal utility of consumption fall? That's a measure of how curved that utility function is. That's intuitive, right? It's a usual elasticity concept. And you can also write it like that, right? Okay, so given that definition of the coefficient of relative risk aversion and the Taylor approximation, we can write this gap in marginal utilities that we're trying to recover as u prime prime over u prime times ch. Again, we're just evaluating this thing at ch. Times delta c over c. And what delta c over c is the percentage drop in consumption from the high state to the low state. And so then coming back to the point of where you evaluate this Taylor approximation, you want to measure this percentage drop as a percentage of consumption in the high state, given the way that this has been derived. And so with that notation, the important thing to focus on here is that I can write the gap in marginal utilities as being a function of the curvature of the utility function and the size of the consumption drop between the low and the high states. Just to make sure everybody's following this, let me show this graphically. So we've got CH here, CL here. What are we trying to recover? The difference in slopes of the utility function in the high state and the low state, right? The percentage difference between the slopes in those two states. And what are we saying? Basically, if I tell you how curved this function is, that's what gamma is. And I tell you how far apart CL and CH are, the product of those two things tells you the difference between those two slopes. That makes sense, right? It's how wide apart are you on the x-axis and how much is the function curving. That's basically it. Okay, so if I take gamma delta c over c, then I can recover the gap in marginal utilities that I'm interested in. And so what that means then is if I measure the curvature of the utility function, which is risk aversion, there's a huge literature in economics on estimating risk aversion, and I measure the gap, the drop in consumption from the employed to the unemployed state, then I can say something empirically about the optimal level of unemployment benefits. And so this is the first idea in this literature of how to use sort of a sufficient statistic approach to estimate the optimal level of benefits. Okay, and so this just summarizes that. The optimal level of unemployment benefits satisfies this expression here, where delta C over C is the consumption drop, gamma is the coefficient of relative risk aversion, and this is the elasticity of the unemployment rate with respect to the level of benefits. So the point is, if I estimate these three parameters in a fairly general class of models, I can say something about the right level of unemployment benefits to maximize expected utility. Okay, so a little bit more intuition of this formula. As I was talking about earlier, the left-hand side you can think about as being the marginal social benefit of UI. It's basically a function of two things you'd think of as being quite intuitive. How volatile is consumption across states? So how much risk are people actually facing? And how much do they care about that risk? So suppose the utility function is linear, right? Gamma equals 0. Then I don't care if my consumption is high in one state and low in another. All I care about is average consumption. Then quite intuitively, the optimal level of insurance is 0. It's irrelevant what else is going on. The left-hand side is 0, right? And then the right-hand side relates to the government revenue leakage, basically. As I've been stressing, that extends to a model where people choose n other behaviors and face m other constraints, so this fairly general environment, subject to some, what I see is basically technical irregularity conditions that are not substantively that important. Now there are, what are we assuming that is actually quite important? The conditions that are required for the envelope conditions to hold, which in particular include agent optimization. I think that's probably one of the most central ones. So one way you can think about empirical work on the subject, which I'm going to talk about now for a little while, is that it provides estimates of the three key parameters in this formula. And then we're going to see what the problems are with these empirical estimates and use that to motivate other sufficient statistic formulas for social insurance, which is sort of where the frontier of the literature is now. All right, so let's start with, I think, the thing that's actually the best measured, which is the parameter on the right-hand side here. So as in many other parts of economics, we're, I think, always quite good at measuring distortionary costs, but not very good at measuring the benefits of programs, unfortunately. So the early literature on this subject, going back to the 70s, used cross-sectional variation and replacement rate. So this is the simple idea that some people, remember the shape of the UI schedule that I showed you where it's upward sloping and then there's a cap? So that's going to generate cross-sectional variation in replacement rates, right? Because some people are going to have higher replacement rates um, than others. And so then you can imagine running an OLS regression comparing higher wage earners and lower wage earners, but that's going to be totally confounded by the fact that your variation is collinear with wage rates, and so you don't get an unbiased estimate of the impact of the UI benefit level on durations. So modern studies use exogenous variation from policy changes. I'm going to talk about the estimates from Bruce Meyer's Econometrica paper in 1990, which is very widely cited. And then there's a lot of subsequent literature, which I'll say a word about. So here's the basic setup that's very commonly used in this literature. So it turns out that the way in which UI benefits are typically changed provides really ideal variation for a quasi-experimental diff and diff approach. So usually the way they change benefits is to keep the replacement rate constant. So remember, this is earnings on the x-axis, the size of UI benefits on the y-axis. So usually what people do is you've got this 50% or so replacement rate up to some cap. And what states tend to play around with is the size of that cap. So they'll raise the cap. So what does that end up doing? It ends up giving you a set of workers whose benefits are totally unchanged. And then it ends up giving you this other set of workers who are treated in the sense that they now have higher benefits. And so now you have, what's quite nice about this variation is you have within the same labor market at the same time one set of workers whose benefits have gone up, often non-trivially, and another set of workers whose benefits have really not changed. And they're relatively close to each other. So as long as you're willing to make a common trends assumption about guys making like $30,000 a year versus $40,000 a year, which you can try to evaluate, you're in pretty good shape here. And so this actually turns out to be one case where we have pretty decent and fairly consistent empirical estimates of the size of this elasticity. Yeah?
What about the guys between E2 and E3? Why don't we favor them?
Yeah, we could use those as like a partially treated group, right? I mean, there's a variable treatment intensity there. So it's just going to be a little bit messier to quantify the size of the treatment for them, but yep, you can use them as well. Okay, so let's talk about how this estimation typically works. I want to say a little bit about hazard models so that people know how to interpret these estimates, because that's standard in this area. So rather than doing an OLS regression, the way people usually think about estimating the impacts of these benefit systems on behavior is using hazard models. So what's the logic of a hazard model? It's to look at the time-varying effects of a policy on behavior at various points of the unemployment spell. So what's the idea? If I raise unemployment benefits from, say, $300 a week to $400 a week, typically UI benefits last for only 26 weeks, right? So in a naive model, you might think that the benefits are only going to affect behavior during those 26 weeks. Like if you've been unemployed for a year, maybe it's irrelevant that you got higher benefits from weeks 1 to 26. Or maybe it's not irrelevant because you might have saved some of that money and it continues to affect your behavior. The point is, you don't want to summarize behavior with a single statistic like the duration of unemployment. The better way to think about it is how is UI affecting search behavior throughout the unemployment spell? And the effects could be very different in different parts of the unemployment spell, right? So maybe at the beginning, raising UI benefits doesn't change behavior very much, but as you're coming close to exhausting your benefits, maybe it has a much bigger effect. The point is there could be all these time-varying effects, and you want to capture those, and that's exactly what a hazard model does, okay? So let's define the hazard rate, HT, as the number of people that find a job in week T divided by what's called the risk set, or the number of people who are unemployed at time T. So the way to think about HT is that it's just the conditional probability of finding a job at time T, conditional on being unemployed for at least T weeks. Right? So if there are 2,000 guys in your sample unemployed at week 10 and 100 of them find a job in week 10, we'd say the hazard rate is 5% in week 10. And it's always defined as a fraction of the people who are still unemployed at that time. And you can see because HT is going to vary over the spell, and we're going to model how HT varies with B, we can get a full picture of how the unemployment benefit system is affecting search behavior at these different weeks. So there are many ways in which you might think about modeling HT. The most common specification that's used in literature is what's called a Cox proportional hazards model, which is a semi-parametric hazard model. So here's the functional form that's used in a Cox model. We model HT as some baseline hazard alpha t, alpha sub t, multiplied by e to the power beta x, where x is a set of covariates whose influence I'm interested in characterizing on the hazard rate. For instance, the unemployment benefit rate, okay? So the reason we call this a semi-parametric specification is because the baseline hazards are totally non-parametric. So the probability that you find a job in week 1 might be 7%, week 2 might be 3%, week 4 might be whatever else. There's no functional form on that. So that's what differentiates the Cox model from other hazard models like the Weibull or other types of parametric models where you assume a functional form for the alpha sub t, okay? Here we're just letting that be totally flexible, which is, I think, the best thing to do in this context. There's no reason to impose some form. And then the reason it's not totally non-parametric is because we are imposing parametric structure in how the x's affect the hazard rate. In particular, they have this e to the beta x form, all right? So we allow the hazards to vary freely across weeks and identify coefficients of a variation across spells. So the way in which we identify the effect of the UI benefit is by comparing two different people who have different UI benefits at the same week. So take two guys in week 4. One guy has a UI benefit of 300, another guy has a UI benefit of 200. How do their probabilities of finding a job in week 4 vary? That's what's going to help you identify beta. So let's talk about what Bruce Meyer actually does. So the key covariate that he's interested in is the UI benefit level, which I'm going to call B here. So he models log HT as log alpha t plus beta 1 log B plus various covariates. In this specification, d log HT, d log B, which is beta 1, is the elasticity of the hazard rate with respect to the UI benefit level, right? So if I include as a regressor log B, then the way I can interpret beta 1 is the elasticity of the hazard rate in any given period with respect to the level of UI benefits. And if you want to map this back to the thing that matters in the model, that is the fraction of time that you stay unemployed, or in this context, your unemployment duration, then as a rough approximation, it's useful to note that if you have a constant hazard model, so a model where there's it's like memoryless, in every period you have a given probability of failure, like 5% or something, then it's easy to show that in that model, the expected duration is 1 over the hazard rate. And so it follows immediately then that the elasticity of the duration of unemployment with respect to the benefit level is just negative the elasticity of the hazard rate with respect to the benefit rate. So does that make sense? So what I'm saying is that the expected unemployment duration is equal to 1 over h if the hazard rate is not varying across periods. So that's just an approximation because, in fact, the hazard rate is going to be varying across periods. And so because of that, d log h, d log b is going to be minus d log expected duration, d log b. So it's just a useful rule of thumb to keep in mind, all right? But you can see how more generally, if I characterize how UI benefits affect the full set of hazards, I can recover the impact on the expected duration just by adding up all the impacts, okay? So Meyer uses administrative data for UI claimants, which we actually had even quite some time ago for small samples. So let me just show you how this looks. So he runs a bunch of hazard models of the type that I described, where he's got log UI benefit on the right-hand side. And you can see he's estimating elasticities in the vicinity of about 0.8 to 0.9, okay? So that's what he gets. And then there are a ton of subsequent studies. And I would say the consensus estimate is now somewhat smaller than what Meyer initially estimated, so probably about 0.5. And there's a little bit of debate around that, but it's much, much better estimated than labor supply elasticities. Okay, so I want to mention one other thing, which unfortunately I did not put in the slides, which is there's another methodology that you can use to estimate duration elasticities, which I think has been done nicely in a recent paper by Camille Landé, which is to exploit this fact. Even without a reform, there are sharp kinks in the schedule, right? Like when you cross this earnings level, the slope of the relationship between benefits and earnings changes discontinuously. And so you can use basically a variant of regression discontinuity design, which is called a regression kink design, which exploits the fact that this discontinuous change in the derivative is useful for identification. And so the logic is, if we expect the relationship between durations of unemployment and earnings to evolve smoothly, which seems natural, why would there be sharp kinks in that relationship? So make the assumption that it would evolve smoothly. Then any evidence of a sharp turn in that relationship at this point can be attributed to the effect of the UI benefit system. And so Camille essentially implements that estimator and shows that there are, in fact, sharp turns in the relationship between durations and earnings at that point. And he gets, I think, very credible estimates of the duration elasticity of unemployment benefits, which turn out to be pretty much in line with the Meyer and subsequent sort of estimates. Okay, so you can see how you estimate the right-hand side thing, the elasticity, and there's a rich literature on that, which you can look into further if you're interested. The best survey is the Gruber and Meyer survey. So the consumption smoothing benefits of UI. So thinking about how to measure the left-hand side of the Baily formula. So in a very nice paper in the AER in 1997, John Gruber takes the Baily formula to the data by estimating the consumption smoothing response. He uses the same methodology essentially as Bruce Meyer. So that is cross-state and time variation in UI benefits, and uses the drop in food consumption as the left-hand side variable instead of the unemployment duration. Right? So you can see basically the same setup, put consumption drop on the left-hand side. Now the problem is that data on consumption is notoriously bad. And so he makes do with the best he can, which is data from the PSID on food consumption. So the PSID asks you at an annual level, how much food did you consume in the recent past? And that's the measure that he's using. So he estimates an equation that looks like this. So drop in consumption on the left-hand side as a function of the UI benefit replacement rate. And then he's controlling for all sources of variation in the replacement rate except for the part that comes from law changes. Okay, so he's isolating law changes as a source of variation in the benefit replacement rate. And he ends up estimating a beta 1 of 0.24 in this equation, beta 2 of minus 0.28. So what's the right way to interpret that? What this means is without unemployment insurance, if you extrapolate out of sample, okay, to a case where you don't have UI, which is not actually true in the data, but assume it's a linear function, then the consumption drop would be 24%. Okay, so he's saying, given the variation we see in the data, if we did not have UI, consumption would fall by 24% when people lose their job. In practice, with the current benefit level, the mean observed drop is 10%. So why does that make sense? Because when B is 0.5, we get back 0.5 times minus 0.28, so minus 0.14. And subtract that off of the 24% drop that we would have without UI, and you'd get a 10% drop, okay? So those are essentially the two facts you can think of as identifying that equation. Another way to think about it is that a 10 percentage point increase in the UI replacement rate causes a 2.8% reduction in the consumption drop. So what should you take away from this study? First, I think it supports the view that insurance markets are not perfect, which is actually a debate that has been going on for some time. Should we think of insurance markets as being essentially perfect because people can always borrow from family or do some other private sector arrangement that we may not directly measure in the data? So this rejects the view of perfect private insurance markets, the fact that UI benefits seem to matter. And it suggests that UI does in fact play a consumption smoothing role. But unfortunately, the estimates are pretty imprecise. So I think this has like roughly a t-stat of 2. So the confidence interval spans anywhere from 0 to like 50%. And moreover, for people who've worked with this type of data subsequently, you find that these results are not super robust because there's a tremendous amount of noise here. You don't have that many observations. It's like a couple thousand observations. And so it ends up being a lot of fragility. So I actually think one of the highest potential areas for further empirical work in this area is to do this type of analysis or other related analyses using administrative consumption data. So one of the frontiers in terms of administrative data where we really have not made a major breakthrough yet is in consumption data. We've talked about great data sources for taxable income, labor supply, savings, all this other stuff, but consumption remains quite limited. And you can think about potentially either getting data from credit card companies or value-added tax registers. I think those are two potential sources of a lot of data on consumption, which haven't really been totally nailed down yet. So interesting area for further work. Yeah. Yeah, that's a good question. So another issue here is like basically stockpiling effects, right? That I might spend a lot and that doesn't directly reflect the amount that I'm consuming. I would, what people try to do is focus on particular types of goods where you think it's perishables or non-durables or whatever, and you come closer. But absolutely, there's a distinction between consumption and expenditure, which Eric Hurst has emphasized in a lot of his work. And he argues that that's what drives some of the fluctuations in what we think of as fluctuations in consumption are actually just fluctuations in expenditure. So that's a potential further data concern. But in my view, even getting decent data on expenditure would be a great step forward. So an interesting question to think about is you notice that people are in fact consuming more when you give them more UI benefits. But one thing I want to emphasize here, sorry, I should have stressed it here, is that when you raise UI benefits by $1, consumption is going up by much less than $1, okay? So it's much less than one-for-one sort of pass-through to consumption. And so that raises the question of what is substituting for sort of getting crowded out by the increase in UI benefits. That's relevant because if you think about the sufficient statistic formula, the only thing that enters that formula is the change in consumption. And so the bigger the impact of a $1 increase in UI benefits on consumption is, the more valuable the insurance is. If all the insurance is doing is offsetting other insurance arrangements that you had anyway, it's not as valuable. So it's interesting, just from an intellectual point of view, to understand what are people actually doing such that when you raise benefits by $1, they're only raising consumption by $1, by like, let's say 20 cents or something. So John Gruber has a series of papers kind of filling in the rest of that gap between the $1 and the, say, 25 cents. And there are various channels that he's thought about. One I'll talk about here is spousal labor supply as a potential insurance mechanism. So in this paper with Julie Cullen, they study the behavior of wives of unemployed husbands, and they examine wives' labor supply as a function of the level of the husband's UI benefits. So when the husband has a higher UI benefit, does the wife work less when he's unemployed to sort of fill the gap, right? So, or a different way to think about it is if we did not have UI benefits, the secondary earner would come into the labor force and act as an insurance mechanism. And so if that's the main thing that's going on, then when we provide UI benefits, we're not actually insuring people better, we're just substituting one insurance. Another potential channel, which I think we touched on in an earlier lecture, is that when you have higher UI benefits, People also seem to build up smaller buffer stocks to a small degree. So they save a little bit less ex ante, and again, you're going to end up seeing a smaller consumption. Okay, so so what Gruber does is takes his estimates of the consumption drop and then calibrates Bailey's model. So this, I think the reason this paper is important is it's one of the first papers to connect the reduced form empirical evidence to a formula derived from theory. Not really at that time, I think, thinking about it from the sufficient statistic perspective, that is, realizing how general that result was. But it's an early illustration of combining the reduced form evidence with the model to say something about optimal policy. So, so remember, this is the formula. This is the way he specifies the consumption drop. Okay, so gamma times the consumption drop equals the elasticity. You can see then how you can solve for the optimal replacement rate, just solving that equation. And so that gives him this formula for the optimal replacement rate, where he is making actually an important assumption that I think is not technically correct, as we know now from further analysis, which is that when you write the formula in this way, you're assuming the elasticity and the gamma don't change with respect to the benefit rate. It's as if everything on the right side is a constant with respect to the benefit rate. That actually cannot be true, which we'll talk about later. This elasticity here has to vary with the benefit rate. You can show that in these models. But anyway, he assumes that that's a constant number. So then he plugs in this elasticity, which comes from Meyer type of estimate, and then assumes a 5% unemployment rate, which corresponds to E of 0.95 in our notation. And then you get, plugging in all those numbers, you get this formula here. So the one parameter I've left is the gamma, right? We're going to look at various values of gamma and think about what that implies now for the optimal benefit level. Okay, so the result, which is not surprising, is that the optimal unemployment benefit rate varies considerably with gamma. So of course, if gamma is 1, which is the linear, gamma is 0 is the linear case. If gamma is 1, you're still at a corner where the optimal benefit level is 0. So what that means is the marginal value of providing $1 of benefits falls below the marginal cost in terms of the government revenue leakage. And so the optimal benefit level is still 0. And then as gamma gets high, you're going to get very high replacement rates. Okay? So Gruber says in his paper, introspection and existing evidence suggest gamma less than 2. And I think that's plausible. So you remember when I was talking about the curvature and labor supply paper, I argued that given labor supply patterns, you can't really generate risk aversion much above 1. That would suggest that you're in this end of the spectrum here, right? Like very close to an 0 optimal UI benefit level. And that's pretty surprising because it basically says, in this context, those elasticities are actually large in the sense that you do not want to have any UI at all given the size of the elasticities we estimate, which seems very surprising given that we actually spend like hundreds of billions of dollars on these income security programs. So I think the Gruber view and the view based on this type of evidence is that the consumption smoothing benefits are just not big enough relative to the distortionary costs to make these types of large social safety nets that desirable. But that, of course, hinges fundamentally on what you think this gamma parameter is. And that gamma parameter is, I think, quite poorly identified in general. So I want to talk about this at a couple of levels. First, empirically, and then thinking about theoretically why gamma might be so unstable. So empirically, there are a couple of nice papers that are just coming out in the AER by Barsegian et al. And Liran Einav, Amy Finkelstein, and co-authors that show you the instability of risk preferences in domains that we actually care about. So they estimate risk preferences across different domains for the same set of individuals. So they look at a set of workers at, say, a big company like Alcoa, where people are choosing health insurance deductibles, prescription drug coverage, disability insurance, 401k portfolio allocations, et cetera. So you're making a bunch of risky choices. And then basically ask, does it seem like people have stable risk preferences across these domains? And the answer, which is consistent with much evidence from the behavioral literature in the past using experiments, is basically no. There is definitely a positive correlation in risk preferences across domains, which they document clearly, but there's tremendous amount of heterogeneity across domains. So there are lots of guys who are picking very conservative health insurance plans, but investing in very risky ways in 401ks and so forth, right? And so that then suggests that the appropriate value of gamma is highly context dependent, which is a result that behavioral economists have been emphasizing for some time. What I want to point out here is it's not just behavioral factors and framing that might affect what the level of risk aversion people exhibit is, but also just standard neoclassical factors. And so let me talk briefly about this paper with Szeidl, which gives you one intuition for why risk aversion can vary a lot across settings. So, and so it's this idea of consumption commitments. So in a standard expected utility model like the one we're working with, we always assume that there's just one consumption good C. So obviously people consume many different things. So what does that assumption actually mean in practice? It's the assumption that there's a composite commodity, or what that requires is that people can optimize on all the different margins of consumption at all times. So in particular, what I have in mind here is that if you face an unemployment shock, the assumption that there's a single composite commodity requires that you can re-optimize your entire consumption bundle when you face this unemployment shock. So when you get unemployed, you cut consumption of food, which is what Gruber focuses on, but the formula requires that you are also able to optimally cut consumption of housing, cut consumption of cars, furniture, and so forth. Now in practice, as you can see quite intuitively, it's difficult to adjust many elements of consumption in the short run because of fixed adjustment costs, right? So if you're unemployed for 8 weeks, which is the typical spell in normal times, you're not going to sell your house and move to a different place. You're not going to sell your car. You're not going to change your kid's school and all this stuff. You would think a lot of things are very rigid. And so you in fact see that in the data. So this is from the paper with Adam Szeidl, where we do an event study of consumption around the date of unemployment using, this is the same data as Gruber uses, basically the PSID data, where you see both food and housing. So in the year of the unemployment shock, so this is plotting food and housing consumption growth rates. In the year of the unemployment shock, there's a sharp dip in food consumption. But if you look at housing consumption, it's a bit noisy, but it's relatively flat compared to food consumption. And this is drawn for homeowners, okay? So this is consistent with the view that there's heavy adjustment on this margin, but hardly any adjustment on that margin. In contrast, if you look at renters, there's pretty significant adjustment on both margins. So it's easier to move for renters than homeowners. And renters do, in fact, cut the amount of rent they're paying pretty significantly when they get unemployed, okay? So that, this is just what we're able to look at in the data, but you might think more generically, there's lots of stuff that people are not able to adjust very easily. And so what does that do to risk aversion, and what does that do to the optimal unemployment benefit level? So this is what the paper is really about. Think about a model with two goods, say food and housing, where the utility function looks like this. It's additive over food and housing. And the key property of the model is that adjusting housing requires payment of a fixed cost K. And so as a result, the agent is going to follow an SS policy where if he looks at his current wealth, and if his wealth goes up a lot, he's going to move up to a better house. And if his wealth falls a lot, he's going to pay the switching cost and move down to a worse house. So those types of SS models have a long history in economics, particularly in macro. But what we want to emphasize in this paper is thinking about what that type of adjustment pattern does to risk aversion. That is, does to the curvature of the value function over wealth, which is what determines your risk attitudes. And let me just summarize the main result with this graph. So if you had no commitments, your utility function would just look like the red, like some gradual concave thing, because you are adjusting on both food and housing throughout. Now, the key thing that the commitment model does is when you're in this range of moderate shocks, like small unemployment shocks that are not going to make you move out of your house, your utility function is going to look much more curved in that region. And the intuition is that every dollar you lose has to be borne completely on a subset of the margins. So it's like if I lose a dollar of income, and I have, let's take this example. Suppose I spend half my money on food and half my money on housing. And suppose when I'm unemployed, I'm forced to cut expenditure by 10%. Then I have to cut food consumption by 20% in order to balance my budget, right? Because the 50% in housing is totally stuck. And cutting food consumption by 20% raises my marginal utility by much more. It's like I'm not able to diversify the shock. I'm concentrating it on a small set of goods, which is driving up marginal utility. And so that makes the value function much more curved in this region as you see marginal utilities going up very sharply. And then you reach a point where you say, you know, I've had enough. I can't cut back food consumption anymore. I'm going to pay the switching cost and move to a smaller house. And then the marginal loss no longer has as steep of an effect on the marginal utility. And so as a result, risk aversion over shocks like unemployment could potentially be very high because you're not able to diversify the shocks. Whereas risk aversion over much bigger shocks like disability, which might make you move out of your house, could actually be much lower. So you can see risk aversion can be super context dependent once you have this type of adjustment pattern. And you know, what we argue in this paper is, you know, maybe the relevant level of gamma for things like unemployment might actually be something like 4 rather than the lower numbers. And then you can see the optimal replacement rates potentially much higher, similar to what we have today. So the problem, you know, the more general problem is that it's very hard to know what the right level of gamma is. And so how can we think about optimal insurance without having to rely on this estimate of gamma is what we'll talk about next time.